Hi, my name is Jason Harlow. Welcome to my V Office Hour. Today I'd like to go over Physics 131 H1S Winter 2011, Term Test 1, and the Freeform question, Part A, which is based partly on the error analysis document that you read in class, and also somewhat on Night Chapter 2, the kinematics in one dimension. But first, let's carefully read the question. In practicals, you attach a fan accessory to a cart, which causes it to accelerate along a horizontal metal track. You release it from rest and measure that it travels a distance of 1.30 plus or minus 0.04 meters in a time of 1.78 plus or minus 0.05 seconds. From these two measurements, and the assumption that the acceleration of the cart is constant, what do you conclude is the acceleration of the cart? Please write your final answer in the box provided with units and error. Both the value and error should have the correct number of significant figures. Okay, so we know that if it's released from rest, the distance that it travels is equal to 1/2 a times t squared. We need to solve for a, the acceleration of the cart, so we can do 2 times d is equal to a t squared, so a is equal to 2 times d over t squared. Okay, so in our case that's equal to 2 times 1.3 divided by 1.78 squared, so it's equal to 0.8206, and the units are meters per second squared. Okay, now the error, we can find from the error in t squared first is equal to the exponent rule, so delta z over z is equal to 2 in this case of delta t divided by t. Okay. So delta z is equal to 2 times delta t times t squared divided by t, okay, which is equal to 2 times delta t times t. The t squared cancels one of the t's in the bottom. Okay, so that's one step. The error in, let's call it y, is equal to d over t squared, is found from the product rule. In this case, we're dividing two things. Delta y is equal to y times the square root of delta d over d squared plus this 2 delta t times t over t squared. Okay, and the error in a, the acceleration, which is equal to 2d over t squared, is going to be equal to delta a is equal to 2d over t squared. We multiply by the factor 2 times the square root of delta d over d squared plus 2 delta t over t all squared, square root. Okay, so this is equal to 0.8206, that's the acceleration, times the square root of your delta d is 0.04 divided by 1.3 is your d squared, and then plus 2 times your delta t, which is the 0.05, divided by your time, which is 1.78 squared. Plugging all that into my calculator, I get the error in the acceleration is 0.052 something 6, I guess. So it's equal to 0.053 to two significant figures, and this is in meters per second squared. So the most precise value of that is in the thousandth column, so that means that I should keep the acceleration also to the thousandth column, so we'll do it there. And so the answer is 0.82, not 0.6, but we'll round up to 1, plus or minus 0.053, and don't forget the units is meters per second squared. Another equivalent way of doing it is we could keep only one significant figure in the error. In that case, you want to put 0.82 plus or minus 0.05 meters per second squared. And probably in this course that would be the preferred answer, but either one is totally correct. So first of all, 0.8 meters per second squared is less than a tenth of g, the acceleration due to gravity. So it makes sense that a cart on a track with a fan on it will be accelerating fairly slowly compared to 9.8. As for the errors, it can be helpful to look at the percentage error of the input variables. So the percentage error in the distance is 0.04 divided by 1.3 meters is 3%. The percentage error in the time turns out to be 0.05 seconds divided by 1.78 is 3% again. So both those input variables have a 3% error. You'd expect the final answer to have at the very least a 3% error, probably more because you're combining those two numbers. So looking at the final answer, 0.05 divided by 0.8 gives you a 6% error in the final answer. So that does make sense. It's a little high, but I think the reason is that you're squaring the t in order to get the answer. And when you square a number, that increases the error by twice as much. So my name is Jason Harlow, and I approve this message.